Welcome at this web event between GrammaTech and Imagix on performing a security review on unknown code. I'm really excited about this webinar. This is a slightly different topic than we typically take on. And John and I are really excited to talk about security reviews on unknown code. Myself, my name is Mark Hermeling. I'm Senior Director of Product Marketing at GrammaTech. I do a lot of discussions with customers on code quality, on code security, and those type of topics. And a lot of my customers struggle with large code bases, and this is how we got to this topic. John, can you introduce yourself briefly?
Thank you, Mark. Good morning, or good afternoon, or good evening, or whatever it is where you are. Thank you for being here. Thank you for your time and your interest. I'm also looking forward to this webinar. I'm going to be presenting a middle section. It's going to talk about the role of reverse engineering and what that plays in the challenge of performing security reviews. I've been involved in the challenges of reverse engineering since my time at Cadre Technologies, which was a case company. The challenge there was to bring source code information into a case model. I'm one of the founders of Imagix, and our focus here is on reverse engineering for program understanding purposes and for the larger issue of transforming your existing source code from a resource drain into a major asset. Mark?
Excellent. Perfect. Thank you very much, John. So let me dive into the meat of this presentation. But before I do that, we would love to make this interactive. So if you have any questions, you should see a little Q&A window somewhere in your user interface. WebEx keeps on changing user interfaces a little bit here and there. So there should be a Q&A button somewhere. Hit that button, provide your questions during the webinar, and there will be a ton of time at the end to dive into your questions, and John and I will try to answer them as good as we can. All right, so let's dive into this then. So what we see, and actually I'll turn the video cameras off as well, that way we have a little bit better bandwidth for people that have bandwidth. So a lot of our customers have this challenge where they are given a large piece of source code, and then they'll have to figure out what the quality of that piece of source code is. And that can either be quality, as in how sturdy is it, how resilient is it, or that can be security, as in how secure is this piece of source code. And if you look at our customer base, there's a split where some customers are truly into the software development lifecycle. And that's where most of our webinar and our blog content focuses on. It's about writing source code and writing the best source code as fast as you can. And that's important. Don't get me wrong, that's an important aspect. But a lot of our customers also do security reviews. And when you do a security review, you sometimes look like this gentleman, right? You've been given a body of source code that maybe you don't understand at all, maybe you've never seen, maybe it's a new release with a new feature that you don't understand. And then the question is, how do you make heads or tails from that piece of source code? How do you get started to understand it? And in the end, what your assignment is, or what your mandate is to write some form of a report that either gives a score, right, maybe between a 1 and 10, on some aspect of the source code, maybe on maintainability, maybe on security or safety. You have to do something. And that's what we're going to talk a little bit about here. I'll take this topic from the static analysis perspective. How can you use static analysis for that particular use case? And then I'll pass it to John, and he'll talk about reverse engineering, and then we'll tie it together. So first of all, I hope, by the way, that if this is your assignment, that you have a slightly better compute environment than this gentleman, right? Everybody knows that if you need to understand large pieces of information, the bigger the screen, the better. So let's dive into this then from a number of different areas. But as I said, this is just a summary of my introduction. You have a large body of source code, right? Sometimes you have tens or hundreds of thousands of lines of source code. Sometimes you have millions. You have little to no architecture information. And this certainly to me has come as a surprise working with my customers. It's unclear as to what is where, what is important. Even if there was some architecture design early on in the software, very often that gets lost or doesn't get passed on or doesn't get maintained. Sometimes you get brand new source code. Sometimes you get a delta, right? And you have to answer the question as in, have we become better in safety? Have we become better in security? And the last bullet is always really interesting to me as well. There's a really short time window. A lot of the people that I've spoken with on this topic have weeks, if that, to perform this assessment, right? So you don't have a month to sit down and say, okay, let's dig into this. You have a week, maybe 2 weeks, but that's the top. So what we're going to talk about here is some tools that you can use and how can those tools collaborate. So going to the next slide here, there's two really main problems that you have to solve, and I call it the whiteboard problem, or the empty document problem, and the bowl of spaghetti problem. The white document problem is you have to write something. You have to figure out where to get started, but you don't really have a framework yet. You've got to figure out and dive into this source code. And then you've got to figure out how everything is connected, right? How is the spaghetti connected? How can you nicely separate that and think of you're eating a big bowl of spaghetti, but you're wearing a white shirt? How can you not become messy in the end? So the three tools that we're going to talk about here is we're going to talk about static analysis, and that's clearly the area that GrammaTech is really strong in. We're going to talk a little bit about reverse engineering, and we'll pass that to John. And then we'll talk about code coverage and how that then connects with static analysis and reverse engineering. And then we'll come back with a number of different summary statements. Again, questions can go in the Q&A box during this presentation. So let's start with static analysis. There really is two different, very different metrics that static analysis helps you deal with. And people typically compare that as the quality metric and the security metric. So the quality metric has to do with how well have you followed coding standards and best practices in the development of this source code. And this is a tricky one. If you've really followed coding standards such as MISRA or JPL or CertC, and that's the team that has developed the source code has stuck to those coding standards, then they can be really good metrics, right? Because it means that you either have or have not been following what you said you would do. But if you have a piece of source code that is not developed with regards to these coding standards, then you cannot really use this quality metric anymore, right? If you take, let's say, Android, which is a large operating environment, right? Lots of C, C++ code. If you would do a MISRA analysis on that source code, which is tens of millions of lines of source code, you're going to end up with a lot of warnings, literally millions, tens of millions of warnings. So that quality metric doesn't hold very much. But if you have a piece of source code that was developed for a car and you're doing a quality assessment on that, maybe it's an ECU, right? Or maybe it's a piece of self-driving software, ADAS, and that was developed with MISRA in mind, then having that MISRA qualification in there is really good. And that's what static analysis does, right? It takes in source code and it validates that source code based on specific rules. And coding standards and best practices, the first part of that rule. So this allows you to really quickly say, hey, I have this much adherence to the standard, or I have this many violations. So that's one really big aspect. The second aspect has to do with security metrics. So this gets a little bit more complicated. So we're talking here about static verification of the source code to find what we call undefined behavior. And undefined behavior, especially when you're talking about C and C++ code, can lead to security errors, right? There's a piece of research by Microsoft that I often quote that says that 70% of the security violations out in the field are due to memory problems, right? Memory problems such as buffer overruns, use after free, those type of things. And static analysis tools are really good at finding these type of problems. They find these runtime errors, they find API misuse, right? Yeah, so maybe you've done a free of a pointer and you still use the pointer. And they can find suspicious behavior. They can find dead code, unused variables, those type of things. So I call that the security metric. And that's what I'll focus on in the next couple of slides. So abstract interpretation is what static analysis tools use for this. And this is a really powerful technique that analyzes the paths through the source code. And it tries to analyze all paths, which is if you have a significant piece of source code, let's say millions of lines of source code, that's completely unfeasible. But what static analysis tried to do is they tried to analyze and summarize the path through the source code. And then based on that, they tried to find problematic areas in that source code. So it's not problematic areas from a requirements perspective, right? Maybe you have a function add, and you add 1 and 2 and 3 is supposed to come out. That's not what static analysis focuses on. It focuses on actual problems with regards to the program language usage, right? So it focuses on memory overruns or floating point issues and those type of things. And the really cool part here is that static analysis does that without the need for test cases. So it tries to calculate all possible paths through the source code, but it doesn't need input cases for that. From that perspective, it's very different from functional testing, right? Functional testing tests the behavior of source code, whether it does the right thing, but functional testing typically doesn't find memory violations. So the goal is detecting undefined behavior, which is the root of many security issues. And GrammaTech has a tool that does exactly that, and that is called CodeSonar. So static analysis is really easy to do. The input really is source code. Well, technically source code in your build environment. But once you have that, it basically is a big compute job to find possible areas of problems. And once you put the input in, once you do the compute job, out comes a list of warnings. And here in the screen snapshot, you see a list of warnings from a particular project that I often use as a demonstration. And for every warning, you get a location, you get like a class category, what type of problem is it? You get a score, which has to do with likelihood, you get a path, and you get a relation to the rest of the program. And I'll dive into each of these aspects of the warning a little bit more in the next slides. So from a location class score perspective, every warning that you see in your source code has a class. So an example of a class could be a buffer overrun. In other words, there is an area of memory allocated to do something in. Maybe it's a chessboard, and the chessboard has 64 squares, and maybe you read or write outside of that 64 squares, right? So that's a security issue typically. That warning will have a location, right? It will be in a file on a line, and it will have a score. And that score is the dangerousness score. So when you do security reviews, this is really important, right? The score is from 1 low to 100 high, and the higher the score, the more likely the tool thinks that A, this can really happen, and B, this is a bad thing. So in your analysis, in your static analysis, if you have millions of lines of source code, it's not uncommon to have thousands of warnings, and that's okay. So those are all areas that you can investigate. But if you're doing a security review, you typically don't have time to go into all these thousands of warnings, right? So you have to go and pick a few and look at a few and understand them, and then use that to guide what you draw on that empty whiteboard that I had earlier. You need to use that to guide what you write in your report. And the really cool part is that these warnings, they can be annotated. So in a tool, in a static analysis tool like CodeSonar, you can actually pick every warning has an identity, and then you can make an annotation. So if you've looked at a particular warning and you say, hey, you know what, this is an actual buffer overrun, and this can be triggered by an external user because I understand how this program fits in its environment, you can make that annotation and you can give that a high warning score and bring that back to the engineers that have written the software. And these annotations can be tracked across builds. So if you get a new build later, maybe one in which they followed your recommendations, you can actually see if these things have been resolved. So it's really cool to annotate this stuff and use those annotations in your report and in your further discussions with the people that you're collaborating with. So the other thing that you get with these warnings is that you get a path, right? Here's an example of a path of one of these warnings. And this warning, I'm not quite sure how fuzzy it is on your screen, but this is a use after free problem. And you can see that in book.c, line 281, which is all the way at the bottom of your screen. You can see that the F read is operating on a file F, which is at the end of that particular call there. And F was closed before, and now you're reading into F. So this is an API issue. You're using something that's free. You have no clue what's going to happen here. This could be a runtime error. This could be a crash. This could be a data leakage. It's really open as to what can really happen here. So all of these things you can take together and decide based on the information that you've gathered how to rate these things. And as I said, you probably have thousands of these. So maybe you look at the highest score warnings and you review the path for those highest score warnings. Maybe you take 2 or 3 warnings per category, and through that type of statistical information, you can get a bit of an overview as to how to rate the problem. Now, John will connect with this as well and help you understand how you can map this to the larger reverse engineered image of your application, which is also really cool. And the last part that we'll talk about here is the relation. So you can see here that readbook, which had the problem, you can see how that fits into the close neighbors in the application. It's not really an entire architecture view. It's not an entire reverse engineered program, but you can see quickly how this fits into the rest of the application. And as I said, John will take a magnifying glass on that and give you much more information about that reverse engineered image. So as I said, static analysis provides one view. It's a really quick way to find lots of information, lots of areas that you can explore with regards to your assessment, with your security or quality assessment. As I said, people use multiple tools. One of the really cool things that GrammaTech has been investing in significantly is the concept of SARIF, S-A-R-I-F. And that stands for Static Analysis Results Interchange Format. And that's a format that allows static analysis tools to generate large amounts of data and then share that with other tools. And that's what we use with Imagix. So that's what we can do. You can take the information that the static analysis tool has generated and then refine that and display that on the reverse engineered application that John will talk about. So from GrammaTech's perspective, CodeSonar can export to Serif and then bring that information into other tools. All right, so that's kind of my part. So let me hand it over to John. I see a few questions come in. That's really, really good. So let me remind everybody, if you have questions, please don't hesitate. Put them in the Q&A. If there's too many, that's okay. We'll respond by email afterwards. But here, let me pass it over to you, John.
Thank you, Mark. That was a great explanation for how static analysis tools such as CodeSonar collect information about potential security issues in the source code. What I'm now going to talk about is how reverse engineering tools are able to help you review this information in the context of the unfamiliar code, so you'll be able to make judgments about the significance of each of the issues identified, how much work might be involved in improving the security of the code, and possibly, if it's third-party code and you have some choices, possibly whether the whole body of source code should be tossed out or whether it should be continued to be used. So in essence, the static analysis that Mark talked about is used to identify what CodeSonar calls warnings, and the reverse engineering piece that I'm about to talk to helps you determine which of those warnings represent actual defects. So reverse engineering means different things to different people, and I'm going to speak from the perspective of our tool. Imagix 4D is a reverse engineering tool, and we divide its capabilities into 5 areas. First of these is, as you see there, program understanding. Sometimes it's called program comprehension or source code analysis, and it's often what people are referring to when they mention reverse engineering. It can involve anything from a high-level understanding of the software's architecture down to detailed analysis of specific functions or variable dependencies. The second item there, delta analysis, you might think of this as a higher-level software diff between versions or variants of the source code. But it's a lot more than diff. It's focused on changes in the control flow and at the control flow level. So delta analysis is to diff, sort of like a sequence diagram is to grep. If you work hard enough, you can get there with diff or grep, but why would you? Design documenting, that's referring to automatically generating accurate, up-to-date design level documentation for existing code. Quality analysis, the fourth point, that includes a set of checks that help verify software quality, ranging from software metrics to inter-task concurrency checks. And program quality review, that's a tool to assist and automate a structured, analysis-driven review of potential issues in the software. What Imagix 4D does here is fairly unique, and I'm going to be describing it in some detail because it's central to how the static analysis results are imported and used in Imagix 4D. But first, I'm going to talk a little bit more about program understanding because A, it's a critical building block of the program quality review, and B, it's quite possible that you'll want to do some basic understanding and exploration of the unfamiliar code before you get to the security review. The challenge with program understanding is that picking up and understanding unfamiliar code is just not easy. You don't know which part of the code you need to study and to read. And even if you could find the right part, there's just too much to read, and it's often very complex. And if you could read it all, there's too much information to conceptually integrate. And even if you could pull it all together, there's just too much knowledge to keep in your head. And so if you don't have the knowledge and you don't have the perspective, you'll be extremely inefficient and you'll be making suboptimal design and programming decisions, and you'll be introducing bugs. So you need a tool. And from our perspective, there's two basic aspects to a full reverse engineering tool, visualization and querying and analysis. So visualization is presenting the information derived from the source code at the right level of abstraction and detail and in a format that's easily understandable, from high-level architecture diagrams, UML class diagrams, down to details of sequence diagrams, flowcharts of what's happening inside of program logic of specific functions, etc. Querying and analysis is the complementary half of this, which is the ability to focus that visualization on the relevant portions of your software. So underneath the visualization and the querying and the analysis is what we're calling our exploration engine. A couple of points I want to make here. The exploration engine ties this together, but what's critical is what comes into that exploration engine. At the bottom in the yellow area is the source code analysis itself. And there, I'd just like to point out that precision in analyzing that source code is critical. The C and C++ languages, there are standards, but then each compiler has its own extensions, and they treat similar things differently, different keywords, etc. And it's very important that the reverse engineering tool understands your source code the same way that your compiler does. The green area shows the import and integration of additional information, specifically results from static analysis and code coverage tools. And we'll see the usefulness of that later. This program understanding is key for working with unfamiliar code throughout the development process. And what we're about to see is that how this holds true for the program quality review. So Mark did a great job of explaining the various standards involved in testing and compliance. Some, as he said, are general quality and safety metrics, and some are security related. Many of the checks that flow from these can be most effectively addressed through static analyzers. You can see the results in lists, et cetera, et cetera. Some of the checks require dynamic testing or code coverage. And there actually is a third category, checks that need to be done in what I would call assisted manual mode. For example, if you're checking the requester for a communications channel, trying to make sure it's properly verified, that's something that you really need to do at a manual level. But for all of these cases, using a tool to automate this wherever possible is obviously very helpful. The first two items there, reviewing software at source code level and mining design level information, those lie in the realm of traditional reverse engineering. The recording of steps taken and the comprehensive reporting, those call for a framework for recording and tracking of the review efforts. And it's to address this need that we've created the program quality review. In Imagix 4D, we actually call our component here the review tool. The heart of the Imagix 4D review tool is the guided checklist. By this, we mean a set of checks that either reflect a set of rules that constitute a given standard or guideline, or we're talking about enumerating the warnings flagged through automatic analysis of the software. So the first of these, the requirement-based checks, we have in the schematic here at the top. These are going to be based on general rules or standards. In other words, they're not indicative of something being wrong, but instead of it's a list of things that should be checked. And this could be standard rules such as MISRA, CWE, Search C, etc. Or it actually could be driven by that delta analysis that I mentioned earlier. The delta analysis identifies where control flow level changes have occurred, and that can be used to guide what should be checked in the next version of the software. The second set of checks, called testing results, are derived from external tools, and that's what the focus is here today, and specifically on the results from static analysis tools. Imagix 4D supports the Serif that Mark mentioned, and that's how we import the results from CodeSonar. Once the checklists are created, then the review tool uses the program understanding functionality that I described earlier, the visualization and the querying and analysis, to examine and analyze the software related to a specific check. It automates as much of this process as is possible, and not just in examining each issue, but in recording observations, making recommendations, tracking results, etc. Let's look at how this works. So on the left, we see a check. And if you look closely, and this is really hard to read, but if you look closely, you can see that it's named variable set in multiple tasks. Within that check, there are two items or potential issues that are listed. And these are warnings that have been flagged by the static analyzer and imported into Imagix 4D as a potential defect. Inside of Imagix 4D, we call these probes. By clicking on one of those items on the left, one of the listed probes, the probe display, the middle display, pops up. This contains a bunch of information showing details about that specific warning or that specific issue. And it's from this probe window that the full functionality of Imagix 4D's reverse engineering and program understanding and visualization and querying and so forth can be unleashed to explore the issue at hand. On the right, we see a call graph that has been launched, and we're able to see how a given variable is used. So in this control flow call graph, we're seeing which functions are calling the variable and all the way up the calling hierarchy. As we examine it, we can make a record of any of our findings as notes. We could could be suggestions for changes, could include just notes about concerns, etc. And at the end of examining this specific warning or this specific probe, we assign a priority. Okay, meaning, we've looked at it, we've examined it, it's not really something that we need to worry about. All the way up to concern, and then a violation, meaning this is serious and needs to be fixed. As we go through this process, the progress, including the assigned priorities, is available for monitoring and tracking. So on the tracking level, what we see is an indication of how many probes exist and how many of those have been reviewed and what priorities have been assigned. The summary also includes these results in architectural context provided by reverse engineering. So on the left, that window on the left is a portion of what we call a subsystem architecture diagram. The diagram itself shows the layering of the subsystems that make up your software. And the layering is all meaningful. The layering goes from top to bottom, showing the layers of the software. Dependencies go from the top to the bottom and to follow the layering. So within this architectural diagram, the colors, in this particular case, are indicating the number of defects or priority probes that have been identified. We use a red, orange, yellow, green scale to indicate the relative counts of defects in the various subsystems, red pointing to the areas of greatest concern. By seeing them within the context of the architecture, we're seeing whether the problematic areas are critical to the operation, how they are linked to outside interference, etc. The graph on the right also indicates defect counts using that same red, yellow, green scale, but here it's within the context of the control flow. Now, of course, any defects are going to be of concern, but if you see clusters of reddish functions, you know that that part of the code needs special attention because there could be dependencies between two problematic areas of the code. So far, what we've discussed applies to your initial pass at assessing the security of the unfamiliar code. But you might remember from Mark's portion of the presentation where he's talking about you've received a delta and are asked, has our posture improved? The review tool has special support for that. This could be a situation where you're checking variants of source code, but more commonly, it applies to where you're checking new versions in maybe a DevOps environment, for example. The typical scenario is you've been handed a software build, let's call it V1. You run the static analysis on it, and then you review those results in the review tool. Then, after some further development efforts, you're handed an updated version of the software, and you need to repeat the process. So what's nice about static analysis is how automated it is. But the review portion does require further steps, and this is where the challenge is in minimizing the review step by using the appropriate results from the previous review that you did, from the V1 review, and using those results for the V2. So when probes from V2 match those from V1, then you can carry over the V1 ratings. And as you can see in the little dialog in the window on the right, there's a dialog, select probe ratings to import. You can choose whether to bring over all the V1 results and overwrite what is there, or just for those probes that you have not yet reviewed in V2. So this is done for matches, and if the code and the underlying derivation change is missing because of code changes, then this will not happen. So code changes can influence the matching that is done and bringing over the previous results. So in summary, the static analysis tools do a great job generating warnings about potential security issues in the source code, and then reverse engineering tools enable you to review those warnings to determine which represent actual defects. And that's true generally across the board for reverse engineering tools. A review tool, like I've just discussed, within the overall context of a reverse engineering tool, automates many steps of this. It automates importing the warnings from the static analyzer and tying those to the reverse engineering tool's visualization and querying capabilities. It automates recording observations and conclusions about the review. It automates making those review results available to team members and to management. And maybe most significantly, it automates making those review results available across versions. So with that, I want to turn this back over to Mark, who will talk about another type of tool for the task at hand, code coverage.
Excellent. Thank you very much, John, for enlightening. So both John and I touched on this a little bit, but there are some areas of overlap here with regards to static analysis, reverse engineering, and code coverage. before I go into that, I have 2 short slides on that. And now is a great time that if you have any questions with regards to John's section, to upload those questions into the Q&A window, and then John and I will address those in a few minutes. So code coverage is an interesting topic. We all know, and I pointed this out before, that static analysis by itself is insufficient, right? You need testing. Really early on in my career, I was talking to a lady, and she was making printers. And she said, I don't need to test too much because my team doesn't make any mistakes, which of course is one opinion. But I think in reality, testing is a good thing to do. Testing both from a static perspective and a dynamic perspective. And that way you test both the correctness as well as the program behavior. So when you do dynamic analysis, though, the question is, are you doing sufficient dynamic analysis, right? There's always more testing that you can do, but how much testing is sufficient? And where do you do it? Do you do like small functional testing? Do you do system integration testing? Do you do regression testing? There's lots of different topics here, which I won't go into. One of the metrics that many people use to make sure that your dynamic analysis is sufficient is code coverage, right? So code coverage allows you to register which lines of source code are being executed as part of your test set of tests. So that's really cool. You can do lots of different things. You can do host-based code coverage, right, where you take your source code and you execute it on a big, heavy computer. If you're doing embedded systems, which many of our customers do, you will want to do target-based code coverage as well. And which means, of course, a whole bunch of new challenges in getting the data to the target and from the target. One really cool part is that, as I mentioned before, static analysis tries to calculate all paths through the source code. So static analysis can actually tell you whether a piece of source code is reachable, yes or not, within a specific level of certainty, of course. But static analysis is really good at saying, that piece of source code that you have here, line 16 to 25 or file b.c, that can never execute because you have an if false before it, or you have an if statement with a variable that can never be true, something along those lines. So when you start doing code coverage, static analysis is a really good tool to start off with and say, okay, well, this piece of code I have to rewrite because I can never cover it anyways. So typically what people do with code coverage is use static analysis, find uncoverable code, remove it, do some tests, write some tests, measure the coverage, right? There's many different tools that allow you to instrument the source code and allow you to execute the program on a host and target, compile all that information, and then you can review your coverage and elaborate your test cases. So one of the things that Imagix 4D is really cool at is that it can, as you saw in some of John's diagrams, it can take the static as well as this more dynamic code coverage information and visualize that. Back to you, John.
Thanks, Mark. So here what we're seeing is the code coverage information brought in the same architectural graph that you saw earlier and the control flow graph that you saw earlier. We're using that same red, yellow, green scheme to indicate how thoroughly it's covered. Again, in the control flow view, if you see areas that are with low coverage and they're together, that says in particular, here's an area that you might want to beef up your testing. On the other hand, from the architectural view, depending on where your testing is low and where your testing is higher within the context of architecture, you might be less concerned about some areas than others, and that will help direct, again, where you want to beef up your testing. What I would add here is on the right is a flowchart for within one specific function. And as you start to get detailed, complex functions, these flowcharts can get pretty large. But within that flowchart, you're able to see which portions have my tests not exercised. And so you're able to say, okay, am I concerned about this? And how do I enhance my test to exercise that part of the code? What I want to show here is that if you remember my early slide where Imagix 4D has the information that's brought in from the source code, but then it brings in the information from the static analysis, and it brings in the information from the code coverage. you're actually able to define your own metrics. Within that metric, it might be some combination of, for a given function, how many defects occurred in here, and how thoroughly was it covered, and how complex is it? In a way that's meaningful to you and your operation, you can define a metric that says, here's where I really am concerned about my testing. And again, you can see those results at the architectural level and at the control flow function calls level. Mark?
Excellent. Thank you, John. So from a summary perspective, before we go into your questions here, there I see a few of them that are actually really good that popped in. Reviewing unknown code is hard. Code is low level, even though it's called a higher level programming language. It's still hard to dig in and really understand the higher level program from it. What we tried to do today is show you some ways that tools can help. We looked at static analysis, right, to find flaws and find areas in the code that you can spend some attention to. And then reverse engineering helps lift that to a higher level. That's really the one takeaway that I had from John's section. And it helps lift it to a higher level, not just from an architecture perspective with regards to what I call boxes and lines, but also from the probes that you can define and the rules that you can define that are important to you or your program, right? It allows you to redo these reviews in a semi-automated and semi-regimented basis. And then we talked a little bit about code coverage as well.